I didn't have to build this hotel myself. Good. Good morning, my name is Halvar. I'm a reverse engineer, and I'm going to speak a little bit about graph-based binary analysis here. Before I start, I'd like to give a short overview about what I'm going to cover. This speech is going to consist of four more or less independent parts. First off, I'll speak a little bit about what graphs are, which is not going to take long. Then I'll try to explain why I like graphs. And then I'll get to actually using graphs as something useful. I'll speak a little bit about simple flow graphing, basically generating flow graphs from assembly or disassembly of applications. I'll speak a little bit about problems you run into when you're dealing with Microsoft optimized binaries. Speak a little bit about how to use these flow graphs for manual decompilation. And then I'll show how flow graphs can be used to evaluate how good a fast tester or some kind of stress testing tool is. Well, afterwards I'll speak about structure and object reconstruction. Basically, explaining what pointer control graphing is something I'll do in that part. And I'll explain what buffer definition graphing is in the fourth part afterwards. Before I start, I have to give a little bit of warning. This is a reverse engineering speech, so it's not strictly security centered. I will not announce any cool new zero today, at least not in this speech. There will be no new vulnerabilities, and some people might ask why this is relevant for a security conference then. The reason why I think it's relevant is because, well, reverse engineering does have many applications in the security world. And the part about code understanding and manual decompilation will come in very handy if you're ever faced with a situation of having to audit binaries manually, like finding bugs in binaries. And certainly it will help a lot if you ever have to decompile a bit of code, for example, a heap implementation. If you want to exploit a malloc override and you don't know what the heap is doing and it's all in binary, you have to get a decent decompiler or a decent understanding of what's going on. Part 3 is very useful for speeding up manual audits because structure reconstruction takes forever if done manually. And some of the concepts in the third part are applicable to a lot of other problems when it comes to finding bugs automatically. So the general principle of the third part can be applied to many other fields. The fourth part is yet another way to speed up manual audits. You can see that I have to audit quite a lot and I'm quite lazy because my speech is all about saving work. And some of the things that are being shown in part 4 do have the implication that they can aid a lot in automated binary auditing, like finding bugs semi-automatically. So what is a graph? A graph consists of nodes and links. That's pretty much how much I'm going to say about this. We're dealing with computer code, so we have a directed graph, meaning that the links only go into one direction. And just to give everybody an idea of what a graph is. Oh, the DJ is better. So, yeah, I still have one. Everybody can see something? Everybody can hear something? Good. Now, why choose graphs? There are many reasons why I personally like graphs. First off, graphs make code understanding a whole lot easier. I'll demonstrate it at some point. Just compare looking at all this disassembly and understanding it to looking at a large flowchart of this disassembly. Well, probably this function was a bit too large. Okay, this flowchart looks scary at first sight, but it is a lot nicer and a lot easier to understand than the original code. So there are control structures, and you can see that certain blocks interact with certain other blocks in certain ways. So code understanding really is simplified by graphs. Secondly, complex issues like, nested loops, complex switches, and so on, are really nasty to trace through in the binary, like if you don't have graphs. And graphs will structure this nicely, and you have a nice picture you can print out and put on your wall, and then look at it and try to understand what's going on. The next good thing about graphs is that pretty much the only valid abstraction for computer code. And as we want to analyze computer code automatically in some way, we need to abstract it first. So graphs are, the underlying principle that goes into any kind of automated code analysis. Another advantage is that graphs have been studied extensively in abstract mathematics. So you have a whole bunch of efficient algorithms, a whole bunch of proofs, and a whole bunch of methods for doing certain things. When it comes to graphs, just get a graph theory book, read for a while, and it should have the answer. And graphs are really easy to generate, and you can use off-the-shelf tools from, like those tools to generate graphs, or to display graphs, like the WinGraph32 one I showed. So there's a lot of off-the-shelf tools which can display graphs, modify graphs, and so on. So you don't have to write your own, display program, and so on. Okay, structuring code as a directed graph is beneficial for both manual and automated analysis. That's basically the reason why I like graphs. And they're so nice and visual. Okay. Applications for simple flow graphs. I mentioned before that flow graphs will simplify code understanding by quite a bit. They clarify code interdependence, and they allow for manual gradual decompilation, or gradual manual decompilation. Another thing is that whenever you're going to try to analyze code automatically or in a more sophisticated manner, flow graphs are the basic building blocks. Because if you ever try, for example, to follow a variable through a function or through an entire call tree, that variable will go into different locations depending on the structure of the flow graph. So flow graphs are like the first building block of everything that's going to come. And IDA 4.17 includes a built-in graphing plugin, which I just showed, or built-in graphing functionality. It does have a few disadvantages, namely that data rescue doesn't give you a way of accessing the graph description. So you can display the graph, but you're not allowed to modify it anyway. It's stored in temporary file, and you have to go to great length to retrieve that file, and it really is not fun. And another problem is that, the IDA provided flow grapher can't handle certain things Microsoft does to the binaries. Building a function flow graph is pretty simple. You just start tracing the code at the very beginning, and you trace the code downwards, and as soon as you hit a branch, like a conditional branch, you split the graph. So you have a consecutive code block of, 50 instructions, then there's a comparison and a conditional branch, like jump 0, jump not 0, whatever. So at that point you split the graph, then you recurse for every splitted part, and you just continue this until you find a node which has no further downlinks, which terminates with the return. So at the end of that, you have a nice, structured representation of the function. It's really easy to build and really fun. I mentioned before that Microsoft does some strange stuff to their binaries. What they're doing basically is, after they've built the entire binary, or the entire, they've compiled and linked it and everything, they start running the program, and they have, a code analysis tool that analyzes graphs of their own functions, apparently. Now, a regular function would be a continuous block of memory. Like in this case, we have begin up at the very top, then some error handler, which is usually not executed but skipped. Then you have the regular code of the function and then the return. Now, you see in those dashed arrows that normally these branches don't get taken. Like a normal operation, only the regular failure will execute. So Microsoft starts executing the program and testing it, and records which are the regular code paths. And then they start optimizing the memory usage by moving the irregular code paths to another page. So you only have the code that's actually being executed in 99% of all cases on one page, and it minimizes the working set you need in memory at once. So you have a smaller footprint for the application in memory, and this will help a lot when it comes to prefetching too, apparently. Otherwise, I wouldn't understand why people go to that great length just to save a few kilobytes. But part of this is it breaks the IDA internal flow path completely. Because for IDA internal, the function has to be a continuous block of memory. Now, I spent quite a bit of time in Microsoft binaries, so the IDA flow graph is pretty much useless to me. And due to that reason, I've built my own flow graph, which was unfortunately x86 specific. Due to an unfortunate accident, I lost all my CPU independent code recently. But nonetheless, for x86, you can generate nice graphs from fragmented functions too. I'll demonstrate this in a second. Okay, now here we have output of 3 group in a URL. Now if you look at it, the IDA generated flow graph has a lot of loose ends here at the end. And normally, a correctly graphed function should have a diamond shape, meaning it starts out in one deterministic location, branches out widely, and then collapses again to one deterministic end. So you can see here that this flow graph obviously is not correctly generated. And when we try to read this flow graph, we will constantly end up in some dead end where the IDA has lost track. So by comparison, if I use my old tool, I just move it to the beginning of the function, hit Alt-9, and then I have to open it. Whoops. We will get a nice and complete flow graph of a function. To even beautify this a bit, there should be an unsorted one. Okay. Now, the problem is with those Microsoft binaries that the return instruction cannot end up above the original beginning of the function due to the way they rearrange the function. So the flow graph is not really beautiful yet because it's not completely laid out. Well, ideally we would want the graph to be laid out in a way that the function beginning is at the very top and the function end is at the very bottom. So now we'd still have to manually edit this file. I'll add some functionality for that one day, but I don't feel like it right now. So we search for the return, and then we assign it the vertical order of, I don't know, 100. And then we reload the graph and it's nicely laid out. We can use this graph for, well, understanding what is going on. I'm going to do that a bit more in a few minutes. Well, these graphs help with manual decompilation. And manual decompilation is not fun usually, because well, you have this huge function there at times, and you have to read it all, understand it all, and then you have to generate working C code from it. It takes forever, and it's very frustrating because you don't really see how much you've proceeded. You get lost easily because you there's one branch which you look at, and you say, okay, I'll look at that later. You forget about it, and you lose like an entire code branch of the decompiled version. So it's very easy to scrap and decompile a large function because a small mistake will screw you badly. And if you ever quit decompiling for a day or two, like this function, and you come back to it, you're like, oh damn, where was I again? So well, it is useful to have some kind of way of keeping track of how much code you've covered, which ones you have, which part you've understood, and then knowing what you've missed, what you haven't missed, and so on. So personally, when I decompile, I use graphs as a visual aid. Whenever I've analyzed the node, I'll color it in the graph, and well, I'll start working my way from the outer layer of the graph inwards. So basically, if you see up here, the beginning of the function, and then the outer branches here, you can see that these are most likely some kind of error checks. Like, if something, then return 1. If something, then return 2. So you start with those outermost layers and slowly peel them away, like peeling an orange or whatever, just layer by layer. It's more an onion than an orange. So you slowly reduce the graph more and more until it becomes simple. Because right now there's a few internal loops in here which I wouldn't understand directly from looking at the graph. Now, all theory is gray. Here we have the nice graph of RTL3 loop. And the first node here just does some standard setting up and initializes a few variables. And then you can see at the very bottom that the pointer to the block we're filling is moved into EDX, where it's being checked to be 0 or not. And if it is 0, it branches out to the far right here and moves 1 into ERX, and then it returns. So a rough recompile of this without the variable initialization would look like this. So we color that in and remove it. And then there's, we probably want to do this in the file to be more visual. So we've colored this node and this node, these two. And now we want to remove the topmost node. We may not yet remove the smaller node because that still has a link from elsewhere. So we'll just uncolor it again and they'll be rearranged in the graph. So obviously the node on the left side there, on the left side of the top node, like the white one, that would be the new top node. So we zoom in on it, assign it for vertical order of 1, 778CB670. Node and the two edges it has. And we relay out the graph, and we kind of have to remove this color here too. So we have simplified the graph by a little bit, and now we look at the next part. These two nodes here in the graph. We see that something is being moved, or the flags argument to RTL3 is being moved into EDX, and then that is being ORed with some flags value from the heap structure, and that is being tested against some bit mask. And if any of these bits are set, this branch here is being taken, and then the function returns. So the decompiled version of these two nodes would look like this. After the block, like after checking whether the block is 0, and if it is 0, return 0, or return 1. It checks for these flags being set, and if they are set, it returns RTL3 heap slowly. So we can get to the next layer. And we can continue this until we're all the way through the function. And this has the advantage of that we always know that we've covered every little branch in that function. We're not missing anything, and we know exactly where we were, so we can pick up on it like a day later or weeks later and know what we're doing. Just the advantages of this approach are, first, if you see progress, that is a huge motivation boost that shouldn't be underestimated. Because if you spend a few days in a large function and sit there and, well, is this ever going to be done? If you see the graph, you can actually sit there and, oh, wait, only 50 nodes to go, only 20 nodes to go, and so on and so on. This is really, well, it helps me at least, because I tend to get frustrated at times. And another thing that helps you to be more thorough in your approach in terms of you are sure you haven't missed any node. Because having a decompile of something and then figuring out you forgot a code branch and this thing behaves differently than you thought it would, that sucks really badly. Another good thing about this graph management is when somebody asks you what the hell you're doing, you can show it to management and they'll understand. Here I'm decompiling. Here are some funny colored graphs. I can even show them in PowerPoint. So it does have its merits. Another not to be forgotten point is that sometimes you have situations which are too complex at first glance. And by peeling away layer by layer, the situation gets simpler. So while you're burning out, the problem gets simpler and less intermediate, which is a good thing as well. I decompiled out to a 3D, I first looked at everything that's colored in red here, and I couldn't understand them in the loops. So I started reducing and reducing and reducing. At this point, the inner loop became quite clear to me, and well, I was done. Any questions concerning the manual decompilation part? No? Good. Okay. So another thing you can do with flow graphs is fuzz coverage analysis. We all know that fuzz testing really is lame, and we all know that fuzz testing really is inefficient, because a minor desynchronization between what the program, like the protocol the program speaks and the protocol the fuzz tester speaks will perhaps lead to entire parts of the program not being fuzzed at all. So you can run your fuzzer for 2 days and always runs into the first error message and returns. Great, we've covered a lot of code. Then you can't really cover, fuzz undocumented features. So if some mail server implements some strange command which isn't even in the IFC, you have no way of fuzzing that one. I mean, you'll not even know it's there. And well, another problem is it's hard to impossible to estimate how good a fuzz tester is. And with all the industry advertising their artificial intelligent common attacking methods, ninja kung fu, I don't know, fuzz tester with artificial intelligence. Yesterday all day in class because they wouldn't give me a wireless microphone either, so good. Well, a good analogy for fuzz testing is trying to shoot bats in a dark apartment. And well, if you sit there all day and shoot wildly, you'll eventually hit a bat. That's pretty much how all the iOS bugs have been found, and well, yeah. Okay, so graphs can be a visual aid here because you can use them to estimate how much code you've covered. And this will work by generating a flow graph of a function or of an entire application, and then loading that into a mini debugger. That debugger will attach to the other process and set a breakpoint on every beginning of the node, like of every graph node. Now then you start fuzz testing the program, and whenever one of the breakpoints is hit, you remove the breakpoint and color that node. So afterwards you have a nicely colored graph, and you can see which branches have been missed. And you can go there and see what has happened there and why this hasn't been fuzzed. This can be used for fuzzer benchmarking, for example. Okay, now we can actually say, I don't know, Latina fuzzes better than Perl. Or, I don't know, so you can compare fuzz testers. Well, it does have major advantages over conventional fuzz because you can measure the amount of code you've covered. You can make sure you cover a lot more code than before. And well, most fuzz testers are scripted in some way. So by looking at the flow graphs and the decisions being made in that graph, like if you see the entire graph being blue and just one like code path and it being white, you just look at the very beginning of the code path and you immediately know where to look in order to find why the branch wasn't taken and so on. So you can adjust your fuzz tester in a way that it'll, well, fuzz that graph too. So the analogy of this is, well, shooting bats in a dark apartment, but at least having a map of that apartment to know you've been in every room. So you don't stand in front of the wall all day and... Right, I think I'll have to demonstrate that. I don't really have a fuzz tester, so I'll just demonstrate how this would work in general. Okay, now here we have a main user input handler in, for an SMTP server, and I'll load it into my small program. Does have a small bug. It converts all links to be blue, but I'll fix that perhaps. So what we can see here is we have the entire graph. What we can see here is we have the entire graph. It's all white. Nothing has been done yet. Our debugger has attached. And we'll now connect to the SMTP server and issue a command. Go. Now, this is the code path that has been taken by this help, apparently. We can follow that through. Well, and apparently, well, we've covered this code here. Now we issue another command. And we see other parts of the graph being colored blue. Well, that's pretty much it. The code should be up for grabs on the Black Hat website, I don't know, today or tomorrow or next week or whenever it's been put online. Any questions concerning the part about simple flow graphing and playing with them? Okay, so let's get into the more experimental parts. Structure and class reconstruction. All information about structures and classes and the layout of the structure internally and so on gets lost in the compilation process. So whenever you're auditing binaries, you really have no clue at all how large those structure numbers are. So if a buffer inside of a structure of like, I don't know, 150 chars, and you have a string copy into that buffer of, I don't know, 1,000 chars, you really don't know how large the buffer is. So before you haven't reconstructed the entire structure, you can't really estimate whether that string copy is going to be any danger or not. So, well, this entire structure reconstruction thing came out of the fact that I used to rebuild structures manually, which worked by manually identifying one of the pointers which points to a structure, and then going through the entire application and seeing whenever this pointer is being accessed, when it's being passed into a subfunction or passed into another register, tracing all the way down. Whenever it is being accessed with an offset from it, add a new member to the structure, and so on. And it took forever and ever and was highly annoying. And
it is made incredibly, or especially annoying by the fact that it's very, very repetitive. It's really stupid. It's nothing that has anything to do with thinking. It's just like stupid monkey work. So at some point I thought that a specialized graph might help, because you could perhaps potentially trace the entire flow of the pointer through the entire application. So if you follow the pointer through the entire code, you can find all accesses to it. So if you find the location where the pointer is being assigned a value, for example, if you have a pointer to a large structure that's being malloc, like the pointer is being taken from the return value of a malloc, then you identify with a point, and then you start tracing the pointer all the way through the code. And once you're done, you pretty much have an exact specification of all buffer boundaries, because you've reconstructed all the structure members. So building such a pointer control graph is not hard. Again, you start tracing at some location downwards, and you keep in mind that, well, you're tracing some kind of register. So you start tracing code at the location, trace down, until you either encounter a local branch, or a write access to a variable, or a read access to a variable, or optionally, if you want to go into the subfunctions, to a far branch, like a call. So when you hit one of those situations, like a local branch, well, for a local branch, you'll just behave as if you're doing a flow graph. You just split the graph as before. Now, if somebody writes to the register you're tracking, you can quit working there, because obviously somebody doesn't need this pointer anymore and is overriding it. Whenever there's a read access to this variable, you have to split the graph again. So if your pointer in EAX, for example, EAX points to structure, that's been moved into EBX, you have to split the graph at that location, and then trace both registers downwards. And if you have a non-local branch, like a call, you can decide to recurse into subfunctions, and, well, see what's going on there. What is tricky on x86, though, is if you decide to recurse and somebody's pushing the pointer on the stack, you have to, well, know, oh, my pointer's on the stack now. The next function will probably take it as argument and so on. The code to do that is really, really ugly. But you won't have these kind of problems on Spark or MIPS or whatever. Okay, so we look at a simple constructor for the IIS HTTP request. In Visual C compiled code, you usually have the this pointer, the pointer to the object that you're currently, well, dealing with in ECX. So what we see here is ECX gets into this constructor, is moved into ESI, and then, well, there's one structure member being accessed here, and then there's a structure member being accessed here, and down here again, and so on. And we can also see that this is a derived class, basically because we see that this constructor is directly calling another constructor with the same this pointer. So for now, we'll just generate a pointer control flow graph for this function without going into any of the recursion crap. For this, I've built a small plugin. Here we are. And you can see all the structure offsets have been converted to structured numbers or variables. The small generated graph for this function looks like this. Basically, you have the beginning of the function where the value is still in ECX. This block here as the first block on the very top. And then the graph is being split because there's a read access to ECX. So the graph continues with ESI and ECX, left and right. ECX is apparently not being read from again, so that node goes all the way down through the entire function. And then we have on the right side another split in the graph, where ESI has been moved into EAX again at location 65F2A whatever. Down here, and that should be a return value. So This is not terribly useful yet.
Have to repeat something.
What you see here is that apparently this function here only accesses these members here. Now, you might ask what that huge buffer in the beginning is. That is the original class from which this one was derived. So basically, we can, by using this object reconstructor in a smart way, see how, well, which object members have, or which class members have been added in a derived object in comparison to the original object from the binary. And what you can do too is you can automatically find uninitialized class members completely automatically by first reconstructing all the structure, running this thing against the constructor of an object, and then running this thing against all other functions all other methods but the constructor. And then you compare the two generated structures, and if there's any member in the structure which you've generated from all other functions but the constructor, which is not in the structure generated from the constructor, obviously they have members in their class which they're not properly initializing. And if you have ever coded C++, you really know that uninitialized class members can screw you pretty badly somewhere. So as we've seen, this has not been terribly useful yet because we've only covered a very, very small bit of code and have only reconstructed 5 members in a class which is, huge. So completely recursing into all subcodes and tracing through the entire call tree, not only through one function, is gravely needed. My plugin has a feature for that too. The only problem is that the graphs being generated with this are not very visual anymore. To automate this for a long time. Now, as you can see, we have a fairly accurate and fairly complete representation of the HTTP request structure or of its internal data layout. We have an array of structures or buffers here. We have sizes that would show up normally, like we have these huge amounts of pointers to all the buffer classes that this constructor or this object or class uses. And now if we ever see a sprintf into a buffer or anything else which could be dangerous into a buffer, we can see whether that would actually be dangerous because we can now estimate the buffer sizes. So this has saved us about, 4 days of work. The next thing we can do with the object reconstruction thing is v-table parsing. Now, a class isn't much more than a structure with a bunch of methods associated to it. A v-table is a table full of methods or virtual methods of that class. So a v-table is really convenient for any kind of reverse engineering because you get a bunch of functions all associated with the same structure. And if you have a bunch of functions all associated with the same structure, you can get a very, very accurate representation, because the more code you have which deals with the structure, the more accurate your presentation will be. So we'll look for a v-table in this application. Here, for example, we have the v-table for HTTP request base. So, well, we've already reconstructed HTTP request, but now look for something else. This hasn't been rehearsed, so if my code crashes, forgive me. But if we're trying to reconstruct W3 IIS service object from its v-table, and basically we just run the plugin, behave as before. And this time you just have to check this nice checkpoint here, check box, not point. And we'll run through and basically call itself for every function in that v-table with the same this pointer, and that'll give you a pretty good representation of the structure. I'm not bothered with this now. All right. So to sum things up, structured data layouts can be automatically reconstructed from the binary by just generating a graph from like a pointer control flow graph and following it through the entire application. By the way, this can be used too for chain graphing, for seeing which parts of the application are being touched by user data, if you just follow the pointer through the entire application. But that's something else. You can automatically reconstruct data layouts by parsing v-tables. Large graphs can be ugly. And something that I haven't mentioned before about RPC interfaces such as like object RPC, such as COM, COM+, DCOM, help us because they publicly export v-tables. I mean, if anyone has ever dealt with that nightmare that's called COM, they have something called interfaces. Interfaces are nothing but a pointer to a v-table. So you get an interface, you have the v-table, first element of that v-table will most likely be a constructor. We'll go through there, and the nice part is you even get like some kind of prototype for that function, because all these object RPC things export well, prototypes for our methods. This automated structure reconstruction speeds up binary analysis by a large factor. Actually, I doubt it's feasible to analyze binaries manually without having object reconstructor if you're dealing with OOP code. Without object reconstructor, you'll get old because, for example, with IIS, you need to reconstruct all those classes manually. So by the time you finish that, there'll be well, 2 new versions of Windows out and a new licensing scheme too. Something that I still wanted to add to this at some point is automatic type reconstruction. Basically, after the reconstruction of the structure is done, I would iterate through the entire application and see whether it's referenced. And for example, if I see well, one of the structure's members being passed into a receive call as a socket handle, I'd automatically reconstruct the type for this and say this is a socket handle. If I see a string copy into a buffer, I'd automatically reconstruct the type and say, hey, this is well, a char buffer. If I see a constructor for another class returning a member of the structure, I could say it's a class pointer, and so on and so on. I'm not going to do that anytime soon because I'm going to rewrite this to be CPU independent sometime, like for next year. And then I might add the type engine too. Any questions concerning object and type reconstruction? Alright, quickly have to check what the time is. -3 you said? Okay. Okay, buffer definition graphs. I'll have to drink some water. Alright, many problematic functions are not dangerous if the target buffer is large enough to hold all the data, of course. But sometimes you have a situation where you have a string copy which doesn't take like a direct pointer to a char buffer, but just a char pointer it has gotten from a function layer more outwards. So if you're in the disassembly and you spot one of those things, you have to trace where this pointer came from. And the reason why I wrote this tool is because I spent 2 days one time, because I had found a strange situation in a fairly large function. I started tracing it upwards where that pointer came from. And I traced, and I traced, and I traced. And after 4 hours, I realized it's a recursive function. So that was bad. So at that point, I decided that there needs to be some way to automate this. And again, specialized graphs will help you. Basically, to generate one of those graphs is you identify the location from which you want to trace upwards, and then you trace the code upwards until one of the following things happens. The current instruction is the target of a branch. The current register is written to from another register. The current register is loaded with something, or the current register is a return value from a function. If that happens, it will follow on. The current instruction, well, if the current instruction was the target of a branch, you have to multi-split the graph. For example, if there's 10 branches all leading to the same location, you have to split the graph into 10 different locations and go upwards from there. So, for example, if you have a function which is called from, well, many locations, you split quite a bit. And if the current register is overwritten from another register variable, you have to start tracing that variable instead now, because the pointer obviously comes from this variable. If you have EAX being overwritten with EBX, you start tracing EBX afterwards. If the current register is loaded with something, you have to analyze the situation. If you can determine it's a buffer load, then this plugin will color the node blue and return and just say OK. This is alpha code, it hardly ever works. And if the current register is the return value from another function, like from a malloc, or from another function which does a malloc, you can decide in the future to either go into that function and see what's been done there. Right now, the plugin will just screen and say, oh, I can't figure this out, and color the node red. Such a pointer control graph would, or such a buffer definition graph would look something somewhat like this. So in this case, we have a bounded string copy, but we don't really care for this because this is just a demonstration. And it takes as a source buffer a pointer to a buffer, and we don't really know where that comes from. It's a local variable. We could now go up here and try to find out where this variable was being written to. Was being read from here, was being read from here, it'll take forever. Oops. Or we use this plugin that I've written, hit Alt-8, select register tracing, because we're tracing EAX, enter that name, and hit enter. A very nice graph, which at the end has a buffer definition. I was just told that I got another 3 or 4 minutes. Alright, so my plugin has found the buffer definition at address 41429E. That's quite elsewhere in the code. And then we can check what the size of this buffer is, and it's 1024 bytes. So we jump back, and we see the target buffer is only 256 bytes, and if this was not a bounded string copy, somebody would be screwed. Alright, I can demonstrate some more, since I still have time. Same thing here, we have another pointer. The graph looks a bit different this time because we have multiple places where it might be defined. In this case, we have a local structure, like a buffer inside a structure. And here you can see it complains because the pointer is a return value from an strchr. And we could just basically patch some code into this to recall itself for the first argument to strchr and patch the two graphs together, and then we could just go all the way through. And the cool thing about this is you find all possible buffer definitions which go into a certain function. So, for example, if you have a buggy logging function somewhere, and you want to know whether there's any location at all where you can put data in there, you generate a graph. And then you iterate through that graph, and for every buffer definition, you check the size. So out of a sudden, you can do constraints. You say, oh, if this function receives a buffer of more than 1,000 bytes, I'll be screwed, or the programmer or the guy who's running that software will be screwed. So you can write a small program which will check all inputs for this function in that program, whether it's going to be that size or not. That's pretty useful, and will open you a lot of doors. And I think the 3 or 4 minutes are over. Any questions? Yes? Well, in a way, if you have a malloc, of course. Oh, the question was whether I can track heap allocated buffers. And right now this thing colors the graph red because it can't deal with malloc heap, but it's trivial to write code to see, okay, if it's red and the core is a malloc, then please take the first argument and deal with that. So tracking heap allocated buffers is no problem at all. Any other questions? Yes? Have not done it. Well, the question was whether I could quickly go over this, how this can be used for security analysis. It can be used to find bugs and speed up that process very much in terms of, well, before it was infeasible to, almost infeasible to audit binaries by hand, or very, very time consuming. And now this is so practical that when I audit source, I frequently compile it with debug symbols and use these tools on them to verify situations. So it helps you with finding bugs and opening computers. Any other questions? Joey, yes? I don't know. Those people that followed my speech last year probably know now that I'm not a very funny guy in the morning. All right, if there's no more questions, thanks a lot.